All right, the next two problems are very similar. The geometry is slightly different, but they're basically the same scenario, which is to say you've got some kind of a bar and it's going to get dropped. Okay, it pivots there at O, but it can drop down like this. But in both cases, there's a spring that's going to affect the motion. So with this one, the spring as it comes down is going to scooch over like that so that the spring is always vertical right over the point A. Okay. Now in the next one, I'll just show you real quick. That's not the case. You can see the spring is fixed here. Okay. But basically this scenario is the same. So let's take a look at this. And probably as you're guessing, that's our best point right there at O. In order to put our pivot. That way we can take into account translation and rotation at the same time because it's the instantaneous center for our system. All righty, so let's get that here. So I0, it's a rod rotating about the end. So we got 1/3 ml squared. And once you put your numbers in on that, you get 180. Okay, it's a pretty massive rod, 60 kilograms, so that's over 120 pounds. So, okay, let's get to our energy equation then. So we've got our delta K, so minus delta U, plus the work done, just like so. All right, and again, like we've seen it a lot of times already, we're going to toss this term, but we've got two potential energy terms that we can deal with, okay? So we've got our minus mg delta y, because the center of mass is relocating relative to the Earth. Then we also have some spring stuff going on here, which is going to be 1/2 k, the spring constant. And now be careful, we got spring constants, and we could conceivably have a radius of gyration in here also. So be careful. Figure out some kind of way to yourself how you're going to keep those K's straight. All right. Because it's bound to happen. You know it's going to happen at some point. Then I'm just going to call this L sub F squared minus L sub I squared, where L is the amount that the spring is stretched. Okay, so it's going to be a little bit easier to use different symbols here this time. So let's break this thing down, figure out delta Y, and figure out the L values, what we need to use for those things. The rod originally is in this position here, and we are interested in when it gets down to 45 degrees. So this thing's rotating down that way, which means that the center of mass has gone from up here to down there. All right, so there's our delta Y from one level to the next, just like that. It's right in the center of the rod, and so you can work this out. The geometry is super basic. So, and it's going to be negative again. We're going to have half the length times the sine of, oops, not 30 degrees, 45 degrees. Okay. And that turns out to be, well, I didn't write it down, but you can figure it out. Okay. So there's our delta Y term. And so we'll use that up here when the time comes. Then for the amount that our spring has stretched, the spring starts out with a certain length up here. Now, we don't actually know what that length is, but we know that its initial stretch is 0. Okay, so it's not stretched at all to begin. And in the end, it's going to be over here It's going to be stretched all the way down to here, and it'll be stretched out some amount L final. Okay. Now, L final is not the top part, not this up here. We don't care about that. We care about this part right down here. And so L final is going to be L sine 45. Right, that. So there's our L final, okay? Okay, initial term is 0. We got 1/2, oops, wrong color. So here we got 1/2 I0 omega final squared minus omega initial squared. That term's 0. Let's see what we get on the right-hand side. We've got minus 60 to 9.81 onto our delta y, which is minus the L over 2. I guess I could do that. So L over L is, the heck is L? 3. So that's 1.5 sine 45 there. And then we're going to have minus k, and our k value is 150. And LF squared then was going to be 3 sine 45 squared. I apologize, I got a little messy there, but I didn't want it to run off the edge into the black since I was writing with black. Okay, when you run the numbers on that, well, let's kind of break it down just a little bit because that's kind of interesting. You can see here that this first term, which is due to the work due to gravity, is going to be positive. So that's the term trying to increase the kinetic energy, whereas this one, the spring energy term, is negative. So that's going to try to act to slow it down as it's moving. Okay, the net effect of all that, the net effect of all that is we get 286.8. And of course, that's joules. And then we'll come back in here like we have been doing so many times. Say that the final there is going to be square root of 2 under 286.8 over I0. And you get 1.785. Okay, and that's radians per second. Okay, so we've seen this kind of a thing before, just not with rotation. All right, so gravity is going to try to speed it up. The spring is going to try and slow it down. So they're competing with their energy that way. Okay, so the next one is very similar. Okay, and we've got almost the same rod. The mass is just a little bit different. We'll still put our pivot where we did before, and we're still going to want the moment of inertia about that point, 1/3 ml squared. Our M term is different this time, but we get a moment of inertia of 22.5. Okay. All right, let's take a look at our energy equation. So we're going to have delta K minus delta U plus any work that's done. And we're going to toss the work term because we don't have any friction like that. And we're starting from rest. So let's just toss the omega initial term before we even get close to writing stuff down here. So we're going to have 1/2 I0 omega final squared. It's going to be minus mg delta y. And we've got that's a spring term again. So we're going to have a minus 1/2 k. And again, let's call it a stretch final squared minus a stretch initial squared, like so. Okay. Now let's go over and figure out about our changes, our delta y's. Okay. So the delta y term, all right, the center has arced, all right, from some level up here down to a level there. So there's our delta y. And we can see then that's just going to be, we need that triangle. So delta y turns out to be 1.5 divided by 2. It's because that's half the length. That's the center point. Okay, so that's my length along here times the sine of, oh, we're going all the way. So that's 90 degrees. Okay. Well, that worked out pretty cool. So that's just 0.75. And it is negative, like so. Now let's get to the spring. Let's see, think about how the spring stretches. So the spring's a little different on this one. It says the spring's unstretched at theta equal to 0. Okay. So let's kind of draw, we're going to curl the end of this thing up, sort of like that. And that means our spring was right here when it started. And at that point right there, that's our initial stretch, and that is equal to 0. Okay. Now, the actual length of it at that point, the rest length, we can know, and the rest length there is 0.5. Okay. We know that it's 0.5 because the rod's 1.5. The distance there is 2. So when that thing is folded up, okay, it doesn't quite go all the way to completely collapse the spring. Okay. So we need the point at which the rod is straight down is here. So that's 1.5. And what we need for our spring then is this length right here. Okay. So that whole length right there is the hypotenuse, is going to be equal to its resting length, which we know is 0.5, but it's 0.5 plus however much it has stretched. Okay. All right. Now, that is we got a 3, 4, 5 triangle there. I don't know if you noticed that. Let me try to point that out for you. Okay. So 3 times 1.5, 4 times 1.5. And that means that this side over here is 5 times a half. Okay. 3 times a half, 4 times a half. The diagonal is 5 times a half. It's a 3, 4, 5. Okay. So that's equal to 2.5. All right. So let me pick that up down here. So that means LF, if we do a little bit of algebra, is 2.5. That's the hypotenuse, minus its rest length, which was 0.5. So that just turns out to be 2. Okay. All right. So let's plug in some numbers here. Get back to our regularly scheduled equation. Our mass was 30, 9.81. This was minus 0.75, minus a half. The spring constant is 80. LF we found to be 2. The initial is 0, just like that. And we've got the same kind of situation. Again, you can see gravity is going to try and increase the energy in our object, while the spring is going to try and slow things down. Okay, it's going to pull some energy out. Okay, when you run, How many times have I done that? When you run those numbers, what you're going to get here is 60.73 joules. Okay. All right. Finish it off like we always do. 2 on 2, 60.73 divided by I0. And so that final angular velocity becomes 1.785 radians per second. Okay, so both of those are very similar. The geometry is the only difference in those, but they both deal with trying to gravity adding energy to the rod and the spring trying to pull energy out of it as that happens. Okay, all there is to it.